Today we are between two important events when it comes to Jupiter exploration with space missions. There's the event that has recently passed, and that will be the focus of our webinar. Of course, it is the Lunar Earth Gravity Assist by the Juice spacecraft last August, and the more than 1 year in space now of the Juice spacecraft. The other event is still a little bit in the future, and that is, of course, the launch of Europa Clipper, which will hopefully take place on the 10th of October. Clipper and Juice will be in the Jovian system together in the 2030s and will be allowing, if all goes well, for some unprecedented science to be done. And the two missions will be closely collaborating, of course. Also today is the release of the latest short film about Juice, episode 1 in the new season, so to say. We have called the season The Journey of Juice. The first season was, of course, The Making of Juice. The link to the video on the Juice YouTube channel will be posted in the chat here. And on Monday, it will also be available on the ESA general YouTube channel. So today we have 3 excellent speakers with us. We have Angela Dietz from the Juice Space Mission Operations team at the European Space Operations Center in Darmstadt. We have Claire Vallat from the Juice Science Operations team at the European Space Astronomy Center near Madrid. And we are also joined by Marco Pinto from Radiation Hardness Assurance and Component Analysis at the European Space Research Technology Center in Noordwijk. And he is heavily involved with one of the instruments on Juice, the RADAM instrument. So Angela will be the first to present, and she will talk about the Lunar Earth Gravity Assist, or LEGA for short, from a navigational and operational point of view. Angela is a spacecraft operations engineer at ESOC. She studied physics at the University of Vienna in Germany and then decided to apply her skills working in the area of interplanetary mission operations, which she has been doing for almost 20 years. First, she was involved with Rosetta. Then she worked for 12 years on Bepi Colombo. And now, 6 years ago, she joined the Juice flight control team. Next in line will be Claire, who will talk about the LEGA from a science instruments operations point of view. Claire has been operations scientist on the Juice mission for 9 years at ESAC, working on the development of this very complex science planning. Unfortunately, we have some years ahead of us to get that completed. Also in the video, she talks about that a little bit. She holds a PhD in plasma physics from the University of Toulouse. And before joining the Juice mission, she was a research fellow at ESTEC with the cluster team, which is also now a legendary mission and coming to an end. And then finally, we'll have Marco, who will talk about radiation and how radiation can be a showstopper for space exploration and what we do about it to monitor it on Juice. Marco holds a PhD in technological physics engineering from the Instituto Superior Técnico in Lisbon. He spent most of his early career helping develop the radiation hard electronic monitor, RADEM, which is flying on the Juice mission and about which we will hear all in his talk. He was also involved with the flight analysis of the Bepi Colombo environment radiation monitor, so similar but on Bepi Colombo, and worked on the radiation studies for Juice and other Earth orbiting missions. So Marco has been in ESTEC for 2 years as a research fellow, and he continues to work with the Bepi Colombo and the Juice in terms of radiation. Okay, after the talks, there will be a time for questions. So please do post any questions in the chat or in the Q&A box, and we will take it from there. So without further ado, Angela, the floor is yours.
Thank you. So let me share the screen. Okay. Okay, so you see my screen?
Yes, it looks all good.
Okay, perfect. So I'm going to talk about the operational aspects of the first flyby of Juice, the mission, to Jupiter, and that's why I just want to give a quick reminder where we are going actually. So yeah, we gonna visit a very interesting planet. It's the biggest of the solar system. If it would be a little bit bigger, like 80 times bigger, so it could have become the sun itself. And the Jovian system is a bit like a miniature solar system. It has a lot of moons, 90, but more and more are getting discovered actually, and the ring system and the very strong magnetosphere. So very fascinating planet. But Juice is actually not so much looking at the planet Jupiter, but more at the moons. So we have, well, very popular are or well known are the 4 large Galilean moons. There's the volcanic Io, which is very close to Jupiter. The radiation is a bit too high. That's why we're not gonna investigate too much on this with this mission, but we're focusing on the icy moons. So there's Europa, Ganymede, and Callisto. They are similar in a way that they have a thick ice crust of several kilometers, and below this, there's a lot of water. And it's really a lot of water. So if you see with Ganymede, for example, yeah, the current investigation shows there might be more water than on Earth, so 6 times more water than on Earth. And it's quite a stable environment and for life to develop, because life needs water, needs some essential elements, some energy which comes from Jupiter itself, and then this stability. So these places, these 3 moons, the environments where life could have emerged, and this is the goal, the science objective of the Jupiter Icy Moons Explorer mission. Also, these moons are very large, actually. They are, for example, Ganymede is larger than planet Mercury. So it's really like, yeah, a small solar system. And at the end of the mission, we're going to go around Ganymede in orbit after a couple of years around in the Jupiter system. So on Juice, so it's yes, it's a large mission, L1 category mission of the ESA science program. Was selected in 2012, and it took 11 years to build and to test, and then it was launched in April last year. So now with almost 1.5 years of yeah, being in orbit or being on its way to Jupiter. It's a big mission. It's around 6 tons, and more than half of it is propulsion. And yeah, it's expensive, so yeah, we are trying to take good care of it on its way. So I'm not going too much into detail on the satellite itself. One of the prominent features is that you see it has huge solar arrays, so 85 square meters of solar array, and this is just to get then enough power when in Jupiter orbit. It will be quite low at this point, so around 700 watts. And so far, these are the biggest ones which are currently flying outside of the Earth orbit. And yeah, so on the instruments, there's a full suite of instruments, of science instruments, looking at all various kinds of aspects of the electromagnetic spectrum, for example. And also there's a magnetometer, there's a particle detectors, laser altimeter for Ganymede observations, and a radar, which has a very long boom here, the Rhine boom. And yeah, it's so, and we are switching on the payloads currently in the cruise phase every 6 months, and the Earth Flyby was a good opportunity to also do some testing, some calibration at the moon and at the Earth. So currently, yeah, we have a long mission, so it takes 8 years to go to Jupiter. We cannot go on a direct route to the planet, so currently there's no rocket large enough to do a direct trajectory to Jupiter. So we do a few diversions, and we use the gravity forces of the planets for these flybys in order to gain energy and to gain velocity to reach at the end Jupiter. So we have, yeah, we had the first Lunar Earth flyby just now in August. Next year we pass by Venus, and then 2 more Earth flybys. And then only at this point we have gathered enough energy then to really go out to Jupiter. We are just completed like 70% of the cruise, so still a long way to go. We're still close in the vicinity of Earth and the Sun. Yeah, so okay, and then I'm going to talk about this Lunar Earth Gravity Assist. It was the first time this was accomplished, so nobody had done this before, and it has some risks because the flybys are very close to each other. So it was like 24 hours only apart, both flybys, and yeah, so the geometry was very interesting, I find. So the sun was on the right side, basically. So the spacecraft, the moon, the Earth, and the sun were in one line. So the spacecraft approached from the dark side of the moon. We had an eclipse also and a communication disruption at this point. Did the moon flyby and then went further to the Earth. And we do this gravity assist because they're very efficient in terms of energy transfer. And also, so we do them to gain energy, well, to accelerate or also to brake. And in this case, actually, we were braking because our next goal is Venus. So we had to lose energy in order to go inside the solar system. And as part of this, also not only the braking, but also the change of the orbit direction. So we did the deflection of 90 degrees. And now we are on the way to Venus. Okay, some slide about the constraints that we're having. So inside the solar system, we have a lot of constraints on the spacecraft because it was designed for cold space. But now, yeah, we are on the way to Venus, which is very hot. So basically, we use the high gain antenna, which is a body-mounted antenna, not steerable, as a heat shield. So the antenna is 2.4 meters large, and it's always pointed to the sun. The only degree of freedom is to have a rotation around this axis to the sun. And this we optimized then for the LEGA for payload operations, such they could look at the moon and then also look at the Earth and do some nice pictures and nice science. And there's another constraint which had an impact on the LEGA this time, was when we were going past the Earth. We had to switch off the communication system, the transmitter, because it's usually radiating at quite a high power, and this is not allowed when we are close to the Earth. So around the Earth flyby, we actually had 8 hours of no communication. This is a video of the flyby. So as said, we approached the moon from the dark side. And we were like then, yeah, passing by around 750 kilometers distance from the surface. And then 24 hours later, we went to the Earth. There were a few opportunities then to change the trajectory, so the attitude, and this was done. You saw this just now with a flip, such that really the face of the payloads could look at the Earth, and we went over the Pacific side of the Earth. And then later on, there was another flip. So wait. Then the next slide. Okay, a bit of navigation. Okay, so some text here, but just to say, this is quite a special kind of flyby. There's not a lot of time to interact. And really small errors at the moon swing by could have led to really large errors at the Earth. And yeah, so if you're really a little bit off at the moon, this could have led to almost mission loss. Yeah, so because imagine you hit just a few kilometers off target, and then the deflection is not 90 degrees anymore, but 60 degrees, and suddenly you end up completely somewhere else in the solar system. But okay, so the navigation had a really important aspect on this flyby. So we started with a navigation campaign 6 weeks before and had a lot of passes, a lot of contacts with the spacecraft for orbit determination. Lots of passes, also with different ground stations at the same time. But the navigation was super accurate. The spacecraft also was very stable. We had a couple of correction maneuvers that were planned. At the end, we only did one 4 weeks before the flyby. And this was enough then to keep us more or less on target. We also had a few emergency slots identified for maneuvers, and also those that were not necessary. So that was quite a big relief. There's a plot here showing the B plane. The so-called B plane is like the body plane of the moon plane intersecting with the orbit plane. And the black cross shows the target, the perfect target, and the red one where we actually ended up. So there was 2 kilometers off from the optimum target, but this was still very, very accurate. And these ellipses here, the so-called arrow ellipses, they show the orbit prediction from starting from 4 weeks before, then 2 weeks before, 1 week, and several days, and they were always pretty accurate, and they didn't change very much. Also, so at the end, it was near perfect, actually, this flyby from our point of view. There's only a little bit of correction which has to be done afterwards, but this is not much. And also another aspect at the Earth flyby, which is important to consider, is that there are, of course, satellites in the orbit around Earth, and we went down to 6,800 kilometers. So we're passing through a couple of orbits. And there's a standard screening for collision avoidance with other satellites, but luckily this was also fine, and we didn't have to do any maneuver to avoid this. So on the flyby itself, so spacecraft was near perfect, was showing no problems at all. The moon, we had the closest approach of 750 kilometers, and as I mentioned, there was an eclipse. So a power. We had to rely on the batteries then for 32 minutes. And the spacecraft at this time cooled down a little bit, but not very much. It was not a long eclipse. And the payloads, they were allowed to operate around 2 hours of the closest approach, so -1 + 1 hour. And this ensured 15 minutes of visibility for the remote sensing instruments. We didn't expand this period for payload operations because the rest of the time was more focused on the navigation itself and the spacecraft safety. And then at the Earth flyby, as I mentioned, this also went over the Pacific. It was outside visibility at this point, but when the spacecraft came back, there was really nothing wrong with it. It was completely fine, very well performed. And for this, we also had payload observation slots. They were a bit larger, so we started 4 hours before closest approach and went up to 3 days afterwards. And now, we are on our track to Venus, which will happen in less than a year. And this is the end of the talk. So I think I can hand over to Claire.
Yes, thank you so much. There's one question, but we will keep that for the end.
Okay, let me just share my screen.
Yeah.
Okay. So apparently,
Yeah, we see something. We see your screen.
Okay, so that's okay then.
Yeah,
I
if
had
you
a
do
weird message, but it seems okay.
There we go.
All right. Okay, so can you see the screen okay now?
Yes.
Okay. Yes, so Angela presented the complexity of the spacecraft operation. So as you can hear, this was really the top priority was the safety of the spacecraft and to make sure that they will actually put us on the right track to go to Venus and then eventually to Jupiter. But of course, we have on board 10 state-of-the-art instruments that could take advantage of this double flyby for very key calibration activities. This is basically this LEGA flyby was a unique opportunity in many aspects. First, because we flew very close to the moon, which is an airless body, so which is some kind of relatively representative of what we could expect at Jupiter with the flybys over the icy moons. There's also a very well-known in situ environment. We know very well the magnetosphere of the Earth. There's many data already acquired, and the same for the moon. So basically, we wanted to take as much advantage as possible of this to perform also those key calibrations. As a side note, there's also several cameras on board of JUICE. So here I've displayed, although maybe I should remove this. Yes, I've displayed for information the JUICE monitoring cameras. So there are two cameras that were initially here to check the deployment of the different appendages after the launch. So if you remember the RIME antenna deployment problem that we had, the camera were actually very useful at that point. And we have, of course, the navigation cameras on board as well. We have also the radiation monitor, as I think Martin mentioned, but I will leave it up to Marco to describe in much more details this instrument and the data of the LEGA. So what I'm going to show here is just some kind of snapshot of the data, of some of the data that were acquired during these double flybys. This is not complete, and of course, this is quite recent, so the teams are very busy now analyzing the data they have been acquired. But overall, in a nutshell, I could say that from an instruments perspective, it was a very successful flyby as well. So let me just, okay, so this is the real data. So you've seen with Angela's presentation that we had simulation of the flybys, but here this is really the JUICE monitoring cameras images that were put together during the flyby. So this is the second GMC, and you can see that given their large field of view and also the fact that they are positioned differently from the rest of the remote sensing instrument, they have actually a different view of the scene. So this is the flyby of the moon coming from the night side, as Angela was saying. And then 24 hours later, we arrived at close to Earth, where we also arrived from the night side and flew over the Pacific. So you see that the cameras that were not supposed to be really used for anything else than monitoring are actually providing very exciting images. And what you could see that I didn't mention is that in the foreground, you can see some element of the spacecraft, like the RIME antenna or one of the Langmuir probe of the radio plasma wave instrument. So now moving on. Oh, sorry, the display is not very good here. That's a problem. Well, whatever. So those are the data acquired not by the JUICE monitoring camera, but by the navigation cameras. So the navigation cameras will be extremely useful when we will be at Jupiter to navigate within the Jovian system. And although they were not directly used during this LEGA during at least this time, for navigation, they were used to take data to test also the capacity of the cameras and especially the functionality of the limb detection, as you can see here at the bottom, which is let's say a way that the NavCam will be operating at Jupiter, because it will use the position, the detection of the limb to position the spacecraft with respect to the body. and to then adjust the pointing, the nadir pointing, to make sure that we reach the right accuracy for the remote sensing instrument. So this is some kind of autonomous navigation system that will be performed, and this was the first test that was done with the moon here. At the bottom, if I'm not mistaken, this was taken close from a point above the Apollo 11 landing site. So moving on to the science payload, more than the cameras on board. Here is the Janus camera on board Juice. And you can see, for example, in the middle, an image that was acquired when we were close to the terminator. So as soon as we were crossing the terminator, the Janus camera, or even a bit before, the Janus camera started to operate. And you see that with this kind of configuration and illumination, you see a very, very impressive, at least to me, level of details of the moon surface. So those data will be used for also for calibration purpose, to check like the radiometric calibration, geometry, stray light, and all this kind of calibration that for which really having such kind of targets is absolutely key. Still with the Janus camera, this is some of the data acquired during the Earth flyby. Where you can see on the left, the dark spot here is the Hawaii Islands, and in the middle you see the part of the Philippines Islands, and on the right you can also observe the very high level of details and the very, let's say, impressive depths and the shadow of the clouds over in the Earth's atmosphere. Another example of data that was acquired has been taken by the infrared spectrometer, MAGIS, and you can see on the left the infrared images superimposed on the Earth map. And you see that MAGIS, which is a key instrument to actually detect and characterize the composition of the moons and of the Jupiter atmosphere, actually were able to detect typical molecules of the Earth's atmosphere, as you can see at the top. And at the bottom and on the right, those are typical images taken during these flybys. The first one on the right is actually acquired during the terminator crossing. So that's why you go from the night side to the day side, and you see some changes in the illuminations. And the one in the middle at the bottom are data taken over the Pacific Ocean at different wavelengths. And at the bottom, this is the thermal infrared wavelengths. So you can see also information about the temperature. So again, those data are being analyzed by the teams. This is a long and slow process, but as you can see, the overall acquisition of the infrared spectrometer were actually very exciting and above expectation from the teams. Okay, another set of snapshot of data, very successful data that were acquired during the Earth flyby. So on the left, you can see the geometry of some observation taken by the sub-millimeter wave instrument that provides information regarding the gas, the composition, and the structure and the dynamics of the atmosphere. The blue dot represents the field of view of the instrument. So it was scanning the limb at the time of the upper left image. And you can see that at different frequency range, you see a signature of water and ozones. And at the bottom, you can see a different configuration where SWI was scanning from the south to the North Pole. And here at slightly different frequency, you can see clear signature of isotope of molecular oxygen and also ozones. So that's also extremely important measurement to calibrate the instrument in preparation for the Jupiter phase. At the top, well, moving on, let's say, to more in situ observations. So the top right plot is data acquired by the radio wave instrument, which actually detected several sources of radio emissions from different sources. So sorry that the text is actually not displayed very clearly here. So it's been sonified just for the purpose of illustration, but those radio wave, actually the one that started on the left are auroral kilometric radiation emission from the Earth's aurora. In the center, there's the plasmasphere emission from the Earth. And what you hear now, or what you see and can hear somehow, are the emissions from the sun coronal. So this will be also very useful to characterize the antenna and to characterize the pattern and the intensity of the antenna. And finally, at the bottom, there's also some data from the plasma environment package instrument with the Jovian electron and ion sub-instrument, which measures the ions and electrons environment. And during the flybys, or after the flybys of the Earth, there's several signature of different region, plasma region crossing around the Earth. So we see at least 4 magnetopoles crossing, which is the transition between the magnetosphere of the Earth and the solar wind. And there's also, as you can see on the right, a signature of the bow shock crossing, which also gives very valuable information for the instrument characterization. So again, this is only a snapshot, and everything that you've seen here can actually is actually already available from the different public release that has been out. But the data analysis themselves, they are of course still ongoing. And just to finish, I want to show you what has been acquired on the 9th of September. So that was 19 days after, or 20 days after the actual flyby of the Earth, where we pointed the spacecraft to Earth, and you can see these far-well images of Earth and Moon taken by the Janus Science camera instrument. Okay, so all this data will be available on the Planetary Science Archive in a few years from now, but you can already find at least the monitoring camera data on the archive site. And I think with that, I will give the floor to Marco, who will discuss more about the radiation monitor instrument. Thank you.
Yes, can you hear me?
Yes.
Yes. Okay, I'm going to share my presentation as well. First of all, I just wanted to thank Martin and Calum for inviting us to be here, and also for my colleagues for showing such a nice presentations and setting me up as well. So I'm talking about radiation as a showstopper in space exploration, and of course I'm going to focus a bit more on the Jewish side of things. For those that don't know, there are many sources of radiation in space. The first one usually being galactic and extragalactic cosmic rays. So these are very energetic particles that come from outside the solar system. Then we have our solar particles. So you might have already heard about these. We have your neutrinos, X-rays, gamma rays. And for me, more importantly, we also get electrons, protons, and heavy ions. We also get particles from Jupiter, actually, in interplanetary space. So Jupiter accelerates electrons to very high energies, and they can escape the Jovian magnetosphere and propagate through the interplanetary space. Also, and particularly important for the flyby. You have trapped particles. These are charged particles that get trapped in the Earth magnetosphere. Of course, the same happens for Jupiter. That's why we need to measure the radiation there. And typically this happens for any sufficiently magnetized planet. So if you add all these sources, you see that the radiation environment is quite complex. We'll see why is it hazardous as well. So that's why we need to monitor it. To add some more complexity to this issue, most of the sources are also modulated by the solar cycle. And the solar cycle is basically changes in the activity of the sun. You can see the image on top. It's in January 2019. At the time, we were at the minimum of solar activity. And you see that this image from the sun is quite nice, quite stable. And when you compare it to the one on the bottom, where that was this past May, you see that a lot of things are going on. We see all these magnetic field lines coming outside, coming to the outside of the sun. And this is our current status. You saw that there was actually some event in May that allowed us to see aurora very to the south of Europe. So this is a register of the solar activity as well. And usually we monitor this solar activity also with something that we call them the sunspot numbers. So you can see this is the axis on the left. That we go up and down with in terms of sunspot numbers, and you see that these cycles take more or less 11 years, and we are now reaching what seems to be one of the maximum of the current solar cycle. So we are getting more and more activity as well. How does this affect the environment? So for solar energetic particles, I think it's quite intuitive. So you see in this plot the CN color or the blue color. We have the sunspot number, and then in pink we have particle fluxes, in this case carbon, nitrogen, and oxygen. And you see that you have all these spikes, especially when you have more sunspots. So this means that when we have larger solar activity, we also have more solar energetic particles. So this is something that is at least intuitive. In terms of the cosmic rays, you can see here cosmic rays are mostly charged particles. You can see here protons, helium, oxygen, and iron. And the part that I want you to look more at is that the dashed lines is actually the solar minimum. So we have higher flux during the solar minimum, and the full lines is the solar maximum. So the flux actually decreases during the solar maximum. And this is because the sun itself, when it has more activity, also it can bend the path of that cosmic rays take inside the solar system. So we can basically deflect more of the lower energy part. Hence this anti-correlation between cosmic rays and solar activity. We also have the Van Allen belts here at the Earth. They are also modulated by the solar cycle, even though I'm not showing it here. But here the message that I wanted you to take is that we have both proton and electron belts, so protons on the left, electrons on the right. And the two main differences I think that you can see is that the electrons actually extend much further from the Earth, so we can trap particles much further in much higher orbits, and also that we actually have two contributions to the electron belt. So we have slight something more closer to the Earth and something a bit further, and there's a kind of a slot region in between where the population of electrons goes down. As for the proton belts, this is much more contained. So you can see that the peak is at around 2 Earth radii, while for electrons it's around 4. So the profile it's quite different. But nevertheless, these are very hazardous for spacecraft, as you will see, and they also happen at Jupiter. Here is how these different sources compare in terms of flux. So the x-axis here you have the energy, and the y-axis you have the flux. So you see that for cosmic rays, for example, the ones at the bottom, they go to much higher energies than both the Van Allen belts and the solar energetic particles, but the flux is much lower. So it's here you have a compromise between energy and flux. The Van Allen belts, they are much lower in terms of energy, and the flux is higher than cosmic rays, but lower than solar energetic particles. However, they are more constant than solar energetic particles, which is these dots on top that you can see. So the higher flux particles, this is just one solar event, okay, integrated over 14 days, while the other ones are just fluxes per second, but you can see that we get a very high flux very suddenly, even though during most of the time you don't have this contribution. So it's again a very complex system that we need to look at. Going now to Jupiter, and I think this is the most interesting part of the JUICE mission, is that Jupiter has a gigantic magnetosphere, and actually the source of the particles that are there are neither cosmic rays and are not the sun. In fact, it's Io, so the closest Galilean moon to the planet. That is the starting point of the particles that we have there. So Io actually is quite active. It expels something like, I don't want to make any mistake, but I think something like 1 ton of material per second into the magnetosphere, and then a combination of a very strong magnetic field and a fast rotation from the planet accelerates these particles to very high energies and traps them in the magnetosphere. So this is a substantial difference that we have from the Earth, because on the Earth the particles are coming from outside the Van Allen belts. Also, something that Angela already said, one of the very interesting aspects is that Ganymede also has a magnetic field that could be able in principle to trap particles. So this adds another complexity to the system, which I think is quite interesting. Just to show more or less the profiles, this is very similar to the Earth. On top you can see electrons, on the bottom you can see protons. You can see that as you go further away from the planet, of course the flux goes down, but you can see also that the electrons belts extend much further away from the planet. Also interesting to see that Callisto, it's a bit outside the belt, so it's a bit more protected than, for example, Europa, where the radiation environment is already quite harsh, and the Ganymede as well. Also, you can see that Io, for example, it's already quite inside the radiation belts. That's why it's much more difficult to have mission orbiting this moon in comparison with the others. Now here you can see how does it compare, at least the trapped electrons between Jupiter and the Earth. So the blue line you see, it's the trapped peaked electrons in Europa. So within the model that we use to estimate the particle fluxes for JUICE, and then in red you can see the trapped electrons in geostationary orbit on the Earth. So geo is basically the orbit where you are at an altitude something like 35,000 kilometers, and where the satellite always looks at the same spot of the Earth. And you can see that even at lower energies we already have a substantial difference. But after energy of 1 MeV, something like this, then we have more than a factor of more than 10 times. And the higher you go in energy, the larger this factor is. So this is quite a problem, because electrons can, especially high energy electrons, can penetrate the spacecraft shielding and make radiation effects on the spacecraft. So I'll guess your question could be, why does it all matter? We need who is asking the same thing. So it matters for a variety of reasons. Of course, for planetary science, I think this is a bit more or less intuitive. The fact that we have radiation is a combination from the source, from the mechanisms that accelerate. So it kind of gives us a lot of information on how the planets work. Then also for astrophysics, as Engel said, Jupiter is a mini solar system, and the solar system is it's a very nice. We have a very nice star, so they can understanding how the radiation works within these two systems can now actually help us understand how other stars in the universe work as well. Then, of course, solar physics. I already talked about the sun, but more importantly for me, or at least for my field of study, it's mission reliability. And what I mean by this is that the radiation will affect the spacecraft. It can actually destroy instruments or missions themselves. So this is something that we need to look at, and we'll discuss just after. And then also for astronaut safety. So it's not just the mission or the electronical part or the materials that the mission has that are affected, but also the astronauts can be affected by the radiation. So this is another important aspect of this topic, that we really need to understand how radiation works in space so that we can protect our astronauts. In terms of radiation effects, first talking about components and materials. Here, I'm gonna ask you to picture your phone. So if you have your mobile phone, it can also be affected by radiation. So one of the things that can happen, we call them parametric failures. So this is kind of an aging of your phone. So imagine that you want to adjust the brightness, you want your phone to be brighter, but with the radiation dose, you cannot put it as bright as before. And as time goes by, at some point, everything will be pitch black and you cannot see your screen, which I think you can understand could be a problem for your phone and for the spacecraft. Can also have state changes, and by this I mean, for example, the memory can be corrupted. Some picture that you have on your phone stored for some time, then suddenly it's a blur and you cannot see, this nice landscape that you took a picture. Let's say, for example, of the moon or the Earth. So this is another radiation effect that can happen, and then actually we can have destruction of components. So you see this nice image on the bottom left. Is actually the material broke on the component, and this was because of radiation. So you can see that also it can render the components completely useless and even destroy spacecraft, depending on what is the function of these components. As for humans, I think most people already heard about the increase in cancer risk with radiation. But there's also other kinds of issues like cataracts. For example, this is something that happens very often to humans. And if you are more exposed to radiation, usually you get these kind of issues earlier in your lifetime as well. And then if you have peaks of radiation, like, for example, during solar energetic particle events, then you can actually get acute sickness, like throwing up, being dizzy. So there are a lot of things that can happen to our astronauts. That's why we have the Juice radiation monitor. So this is a very nice image that I took during my PhD, actually. And the Juice radiation monitor, it's not actually going to protect the spacecraft, in the sense that it's not going to send a command to the spacecraft that it needs to shut down at some point, but it's actually a part of a bigger or a larger European Space Agency plan, where we really want to characterize very well the environment, and using this information to design better and to shoot better our mission. So it's a long-term plan that we have. And in the case of Radon, we are actually going to measure the electron spectrum on Jupiter. As you saw, it's quite important, especially the higher energy part. Then we are going to measure the proton spectrum, heavy ion intensity, electron directionality. This, I didn't really have the time to go into many details, but it's also an important aspect of this detector. And then, of course, it can do total ionizing those calculations so that we can estimate how much aging our components are subject to. In terms of the cruise phase, we are kind of fortunate with the radiation monitor, in the sense that it's on almost all the time. And here you can see our observations in September 2023, so already more than 1 year of data. And all these spikes that you see are actually solar energetic particles. So we are currently going towards the solar maximum. So we got a lot of events, which are already a very nice moment to start to calibrate our instrument, and also to start doing some science analysis, in fact. Then the peak on the right, you see, is the Earth flyby. I'm going to show you a more detailed image in the next slide. And also in July, you see there's a big shift, but this is just some reconfiguration that we did to the detector. Also, when you don't have any spikes, what we are actually measuring is the background from cosmic rays. So it's another aspect that we can study with Vallat. For the Lunar Earth Gravity Assist, I'm not going to show you a lot of details in terms of orbit, because my colleagues already did it so nicely. But here you can see the measurements of the electrons. So the white part that you see in this plot, it's the electron intensity from the outer belt. And you see that we measured it quite nicely. The yellow line is the electron observations from Radon. So you see that we actually measured very nicely the outer belt, both when we went in and then when we moved out from this region. Notice that we don't see the inner part, and that's mostly because we didn't reach the inner part of the electron belt. As for protons, we only really skimmed the proton belt. We still were able to observe it, as you can see the blue line. So the outer belt is much closer to the planet. We didn't really go very deep, which in part is good because then that means that we didn't get exposed to all this radiation. But it was just enough that we were able to do some observations, and that will be very useful to calibrate the instrument, since the Earth radiation belts are actually the place that we know the radiation the best, so we can model it quite nicely. And also we have a lot of instruments from other missions going around that we can use to compare the data of radon with them. So I think I can stop here and we can go to questions. Yeah.
Excellent. Thank you so much, Marco, Angela, Claire, for your very nice presentations. Yeah, let's open the floor for questions. There are already some questions that were streaming in, and a few of them have already been answered in the Q&A by Callum and Angela. So, okay, well, they've been answered. Let's see. There was another one by Penelope, and the question is, will other calibrations or tests be performed during the Venus Gravity Assist? Olivier, or anybody wants to comment? You already wrote something, but let's...
Yep, I wrote something in the chat. That basically we have still some internal discussions about that, whether we do some scientific observations during this flyby. The problem is that we have some challenges related to this flyby. The heat environment, of course, Venus is one of the closest point to the sun for the full trajectory towards Jupiter. And also, given the configuration of the attitude of the spacecraft, we have very limited data rate in this period. So that's why it's very challenging to make some observations. So we are still discussing that in the ESA project.
Excellent. Okay, are there any other questions? So there was a comment by Pascal in terms of the navigation cameras to be used for autonomous navigation. Maybe someone can comment on that.
Okay, I can say something for this. So the NavCam, we've only used the navigation camera with an open loop, making pictures, but not yet in the full closed loop navigation sense, kind of. So there's a certain mode of the navigation camera who then can really change then the attitude of the spacecraft. But this only has been validated on ground with one test after launch, actually. We need to do another ground test before we can think about testing this in flight. And the LEGA was such a critical maneuver. That was very risky to do this the first time in flight at this point. So we decided against this.
Okay.
This closed loop navigation will be used at Jupiter. So that's why the development of the mode end-to-end has been a bit delayed to be done during the cruise phase.
Okay, excellent. Thank you. Let's see. I see Ronan Doletti is online and asked, did RIME confirm that they received the RF impingement through the RIME antenna and receiver sent from a telescope in Alaska during the Earth flyby? Right, that was true because, yeah, I remember this. Anybody knows about this?
Well, actually, I just see that Ian has
somebody,
so
yeah.
it was a request.
Can we people to speak as well, or if you want to, Claire?
Well, can I let Jan?
Yeah, I was wondering about that. Is that
so
possible?
We can promote an attendee to panelist. It would mean that Jan would need to briefly leave the session and then rejoin as a panelist. It might take a minute. Would we like to do that?
If Jan would like to do that.
Certainly. Okay. I will invite Jan to rejoin us as a panelist, and then the decision can be his.
He can comment on it. Okay.
Actually, here we go. There may be a new function.
There we go.
Just now allowed him to talk.
All right. So
there we go. That was quicker than it used to be.
Okay, good. Jan?
Okay, can you hear me?
Yes, we can.
All right. So actually, we did an experiment with HARP during 30 minutes during the Earth closest flyby. But there were two difficulties. First of all, the elevation towards use from Fairbanks in Alaska, it was too low. So we had refractions, so they had problems. And furthermore, we had to reduce the power in order to be compliant with the requirements by the RIME instrument. So it wasn't successful. But however, we saw quite a lot of other radio missions from HF radio stations and also possibly from ionosondes.
Excellent. Let's see, there's another question. I saw you posted new images taken from 5.7 million kilometers from Earth. Can you comment what kind of additional calibration tests could be done then?
So the image that was taken from 5.7 million kilometers was the last one I showed in my presentation. Well, I think Janus can use it for additional calibration of the instrument, but it was not the ideal configuration because we were already quite far away. So it was more as a kind of a farewell images as a first let's say goal. But then well, I think that Janus will use it also for a specific calibration of their instrument. Although I'm not sure what else exactly they will be able to use from that distance.
Yeah, I think what you could add also that there were other instruments also being switched on. It was not only Janus, there was also with SWI, so the microwave instrument. Yeah, and a couple of other instruments.
Yeah, it's true. Yeah.
And the navigation camera was also used for interesting testing.
And talking about the testing, because so of course it was mentioned that oh, hang on, we have Jan. Can you tell us more about the spacecraft rotations during LEGA, Angela?
Yeah, so there were these flips that were also shown in the videos. There was one just before the moon in order to have the phase where the instruments are sitting, looking at the moon. And then between Earth and the moon, there was another flip to then have the instruments looking back at the Earth. And later on, one more, and in particular for APWI, where Jan is working at, we did a 360 degrees rotation as well. So.
Okay. So there was a mention that about, of course, the uniqueness of being able to look at an airless body for science instruments. But I think that in the next 2 Earth flybys, or at least 1 Earth flyby, we will not fly by the moon as close as this past flyby, but there will be some moon observation possible, no? In 27?
Yes. Well, I mean, we still have to check the geometry in details, but for sure we will be further away from the moon. And the really unique opportunity in our case here was the fact that we were close enough from the surface to actually operate the geophysics instrument, the radar and the laser in particular. They have quite constrained geometry for operation. They need to be, the spacecraft need to be about up to 1,000 kilometers basically to get an echo for the radar, for instance. So this is the unique opportunity during cruise to have actually an echo from the surface of the moon to be detected by RIME, for instance. Okay. But of course, we will use. I mean, if this is possible, we will use additional observation more for the remote sensing instrument of the moon during the next 2 Earth flyby.
Yes. Okay, we are a few minutes over the hour, I think. Are there any more questions, burning questions at this time? Then I think we can close the webinar with many thanks to everybody, Angela, Claire, Marco, for your great participation here. Yes, we are planning for the next webinar, which will be somewhere in November, for the next JUICE webinar, somewhere in November. Many thanks for all you who attended and all the questions and good discussion. And so I guess see you next time. Thank you so much.